but hopefully we won't be all remote, hybrid, half students, blended, this and that next year. But who knows? Okay, uh, in the course on the right hand side, the salinity and depth activity. If you haven't finished that up, you can finish that up today. The water chemistry lab, we're going to actually do it on Monday and Tuesday. But I want to tell you about how it works now, so that when you come in on Monday, you can just like get ready to it. So if you're remote, the water chemistry lab is in here, and you can like view it. But I'm going to show you also where the data is. So for remote students, there's data that you can use to be able to do the calculations that's similar to what students in the class would get. So where it says water chemistry lab remote data sheet, this has sample data that came from students from the fall who did it like in person. And so there's like sample data, and then you still have to do the math to do the rest of the work. Anyway, so like here, there's like a data table that's similar to the bottom of the first page for remote students, because I can't send home like chemicals and lab equipment and stuff. All right, so a couple things that you want to be able to do. A big deal about why the density of salt water is different at different depth has everything to do with temperature. So water, we've used as a standard in the metric system, as a standard for mass and volume. And it's not a coincidence that the density of water, which you might know from chemistry or biology class, is 1 gram per cubic centimeter or 1 gram per milliliter. And that's because the metric system was intentionally rigged or set up so that water is used as a standard for a lot of things. We rigged it so that 1 milliliter water has a mass of 1 gram. And the reason why that would be useful is if you have like a balance or a scale, you can weigh out water and you know a volume. Or similarly, if all you have is a graduated cylinder, you're like, I want 50 grams of something, but all I have is this graduated cylinder. Well, if you find the volume of 50 milliliters of water, that 50 milliliters of water weighs 50 grams. So that's one of the geniuses of the metric system, is that the density of water is rigged to be 1 gram per cubic centimeter. Yeah.
I saw this temperature comparison thing online. It was like Celsius is asking water what the temperature is, whereas Fahrenheit is like asking a human what the temperature is. And the other one, the third unit, I don't know,
Kelvin.
it's like
Yep.
asking an atom.
Yes. That's a good way to look at it. So the Fahrenheit scale, 100 historically is human body temperature. You know that average human body temperature is, people always say like 98.6. Most people are like in the high 98s, really. But when the Fahrenheit scale was established, like if you're in a lab, you've got stuff around you that you can use as reference for temperatures. The Celsius scale is like, well, what temperature does water freeze? We'll call that 0. What temperature does water boil? We'll call that 100. Now you got a 0 and 100. In the Fahrenheit scale, it was like, well, what's in the lab? I'm in the lab, so I'll call myself 100. You know what I'm saying? But then 0 isn't the freezing point. 0 is when you take ice and you mix an equal amount of alcohol with it. It depresses the freezing point down to 0 Fahrenheit. So if you have ice and alcohol and a human, now you got 0 and 100 in Fahrenheit. So that is true, but and the size of a Fahrenheit and the size of a Celsius are different. But water is so nice. Water is so ubiquitous. It's everywhere. Every lab's got water. Like if you're looking to do science and you don't have water, you're probably going to die within a couple days, because you need to drink water all the time. So the last thing on your mind with if you don't have water, like if you're like, yo, there's no water in my life, I could die in 2 days. You ain't going to be doing no science. You're going to be like trying to get the water. So that's partly why water was used as a standard. So what I want you to do is compare the densities of different kinds of water. So water's density is usually a gram per cubic centimeter or a gram per milliliter. Both with RO water, RODI water, like from the perfectly pure water. It's like room temperature. And then cold tap water. So run the tap until it's like really cold. And then also with boiling hot water, what's the density of those kinds of waters? And that's just as close to pure water as you get. So the easy way to do that is, because you can't just pour water on a balance, that doesn't make any sense. You can't be like, let me get a screen here. New share, open board. Yeah, like so, I mean, here's a balance and it's got the little scale. You can't just start pouring water on the balance because, it just gets the balance all wet and whatnot. So if you weigh a graduated cylinder, if the cylinder has a mass of like 125 grams, and then you carefully fill it to 100 milliliters, like the 100 milliliter mark, it should be that 100 milliliters of water has a mass of 100 grams. So then the cylinder plus the water should be, around 225 grams. And that means that if you subtract the mass of the cylinder from the mass of the cylinder with the water, the difference will be the mass of the water. But 100 milliliters of all water does not all have a mass of 100 grams. Because if it's hot, or if it's cold, or it's got salt in it, it's going to be, it's going to have a different mass. And the density, which you should know how to calculate, is just the mass divided by the volume. And I put that equation on the thing anyway. So you take the mass in grams of the water and divide it by the volume in milliliters, and that gets you the density of water. So the density of cold water, hot water, RO water, they're all going to be pretty close to 1. But salt water from the fish room, its density is not going to be, it's going to be kind of close to 1, but it's going to be a whole lot different than 1, because when you start dissolving salt in water, it has a significantly different density. So one way to tell how much salt is in water is by its density. But measuring how much salt's in water by taking some water and finding its mass, measuring its volume, doing math is, I don't know, I kind of say laborious or tedious. So there's other ways to measure salinity. And these are methods that are used in oceanography by researchers. We use them here in the lab with our saltwater aquariums and stuff. One way is with a salinity meter. So just like you use the pH probes, we have these salinity meters. And really all it is a conductivity probe. There's 2 pieces of metal. And when water has a lot of salt in it, it conducts electricity better when there's not much salt in it. So all you simply have to do is just like take the probe, stick it in the salt water, and it'll tell you the conductivity. The thing about the conductivity meter is that it measures conductivity in a unit, and it's displayed on the screen in parts per thousand. And this conductivity in parts per thousand means how many bits of salt there are per 1,000 molecules of water. But a common thing that we usually use in both aquarium science and in oceanography is another unit called specific gravity. So I put a link to a site here, bit.ly/saltconvert. That's a shortcut link to get you to, oh wait, that's weird. I didn't copy, didn't paste. bit.ly/saltconvert. I don't know why this is goofy. Salt convert. Salt water. Close. Here we go. So this is a real quick and simple converter. You put the salinity value in here and what unit it's measured. So let's say the computer says it's 35 parts per thousand. Then you click calculate and it gives you the value in parts per thousand, this specific gravity value, and conductivity. So here's what specific gravity means. This 1.0264 means that the water is 2.64% more dense than regular fresh water. So pure water has a specific gravity of exactly 1. If it's 1.0264, that's 2.64% more dense than fresh water is. So you measure the conductivity of RO water, tap water. The water out of our tap has some stuff in it. It won't be 0. The fish room water will have a significantly higher conductivity because that's salt water. Another way to measure density is with a device called a hydrometer, and we make them a couple different ways. This is one from a company called Instant Ocean. That's that brand of salt that makes Instant Ocean and reef crystals. And how this hydrometer works, this is very simple. These are very cheap. This is like people who go saltwater fishing sometimes carry these in the boat because if you're in brackish water, you might be fishing for a certain kind of fish that likes water of a certain density, and you're like, oh, I wonder if this is too fresh or too salt. Like if you're around a coastal area, you can measure the uh, density of the water using a hydrometer. So all you do is dip this over the edge of the boat or fill the thing up. You put water in the hydrometer, and the deal is this thing that swings in there, that needle, that pointer has a little weight in it. If the water is perfectly pure fresh water, that thing will hang down in the water, almost straight down. As you have saltier and saltier water, this thing is more and more buoyant and it'll float higher up. And there's a little scale along the side here that both has values in parts per thousand on the outside, but specific gravity on the inside. So we're going for around 1.026, which is right about here, like where my finger is pointing. So wherever the needle points, that tells you how much salt's in the water. I constantly have to make sure that there's a correct amount of salt in our aquariums to be able to, have the saltwater fish like be happy. So you can use a hydrometer to measure the specific gravity of RO water, tap water, and the fish room water. Another instrument, which is actually more reliable. So this thing here is kind of easy, it's cheap to use, but there's issues with it. That plastic thing that hangs down, if there's any air bubbles that stick to it, it makes the thing more buoyant and reads too high. And sometimes it's a little bit sticky in there. This one's a brand new one. It just has a little bit of salt creep on the outside, but it's pretty much brand new, so it'll work well. But when they get old, they don't work as quite as reliably. So another instrument, which is also almost as easy to use, is this thing called a refractometer. I put a diagram in on your lab about how refractometers work. So refractometers measure how much salt's in the water by measuring its index of refraction, which is the amount by which the water changes the direction of light that travels through it. And the more salt that's in water, the higher its refractive index. So how this goes is there's a little door on here. You flip the door up and there's a little prism on there. All you got to do is coat that prism in water and close the door. And whenever it's closed, instead of this thing being like dry and kind of milky looking, it'll be like dark and totally transparent. You can also simply work these by just dipping the thing into water. If you dip it into water, water will cover the glass and be on the plastic thing. So whenever that surface is wet, then you look through this eyepiece. And when you look through the eyepiece, you'll see a scale inside there. The scale, when you look through the eyepiece, will have a section that's blue and it'll have a section that's white, or really it's like clear and colorless. And wherever that line is between the blue and the white, that's where you read on the scale what the salinity is. So for in this example, this thick line here is 1.020. This one's 1.030. So I'd say this is right around 1.020. We're going for like 1.026, which is up there a little bit. There's a illustration about what your goal is. When you look through this part here on the outside, you want to make it so that it's really dark. It's got a lot of water underneath where it says good. If you don't have enough water, it'll be like blotchy or there'll be air bubbles, and it makes it difficult to read. The other thing is you have to focus it. There's a knob on the end and there's a little gap here. And you notice if I turn the eyepiece, it closes the gap. And if I turn it the other way, it opens the gap up. So if you look through there and it's all blurry, like you can't read the numbers and it's all out of focus, all you do is turn the outside. And for most people, once you've got it focused for yourself, you don't really turn it anymore. It's kind of like binoculars. They use binoculars or a scope on a rifle. You can adjust to get it focused, or like a telescope. So that's how that equipment works. So you kind of have a choice of what equipment you use to measure conductivity. If you're a research ship, it's easy to have this thing sticking down in the water all the time. And that way, as you go through the water, it's constantly measuring and you can record the data for conductivity, except these probes are about $100 and you got to have a computer and programs that can record all that stuff. So although everything can be automated, it's a higher cost. These hydrometers are the cheapest things. They're like $10, $8, $10, whatever. Hydrometers are like, they used to be more expensive, but for the refractometers, they're like on the order of $40 or something because it's a more sophisticated piece of equipment. So it kind of depends on like how cheap and easy do you want to do it, and how precise you need to be, and do you need to collect data over long periods of time or whatever. Anyway, that's how that goes. The other thing we're going to do is work with the aquarium systems and work with growing and raising coral and things and cutting coral up and doing some more like, you know, working with our actual fish here. And in water, there's more stuff than just water and salt. Other things that we test include pH. So you've already used the pH probe, and that's pretty easy. But we also have test kits. So the pH probe you'll use to measure the pH. And then the other four things, this is on the back, are there are two major things that we want to keep reduced in the quantity of in our water, and those are nitrates and phosphates. So the nitrate anion and the phosphate anion, those are considered nutrient waste. And it doesn't matter if you're a farmer, if you work in wastewater treatment, or if you're dealing with water quality in a stream or the ocean, how much nitrate and how much phosphate is present are the two most important critical things to know about how much waste is going into the water. As we feed the fish and the fish poop, it makes a lot of nitrates and phosphates. Sewage, as it runs into water, has nitrates and phosphates. Soap puts phosphates into water. And those are used as fertilizers on fields and for crops. But in water, you don't want those levels to be high because it encourages the growth of algae. It reduces the concentration of oxygen in the water. Those nutrients provide like competition for larger organisms. So nutrients sound like a good thing because you need nutrients in your diet. But when we say nutrients in water, we're talking about these negative nitrates and phosphate ions. So we have to constantly monitor how much nitrate and phosphate is in the water and try to reduce it. And the major ways we reduce those quantities of waste is by doing water changes and by using chemicals that can actively remove the waste from the water. And that costs us money and takes some effort. That's how you provide good water quality. The other two things that we have to keep in the water and keep those levels high are magnesium and calcium. So calcium, I'm going to tell you a lot about calcium next week, and it's related to bones in fish, shells for seashells, the structure for corals and coral reefs. Calcium plays a very, very, very important role in life in the ocean. And it also plays a very important role in our aquariums. The magnesium is also very important because without a sufficient level of magnesium, you can't have the calcium deposit well at all. There's another tool, and that's that if we get a bunch of nuisance algae growing, you can jack the magnesium level way up because magnesium is actually somewhat poisonous or toxic to a lot of nuisance algae. So I've provided ranges of values that you want for in salt water. The goal is to have the pH around 8.2 to 8.4 because that's very similar to what the ocean pH is. You should have measured some kind of pH for the salt water before putting acid or base in somewhere around 8, except the pH probes weren't calibrated for that experiment. So there's a change we care about. The goal is to get nitrates and phosphates as close to 0 as possible, but the magnesium can't be too low or too high. So this 1250 to 1350 is a good range, and the calcium 400 to 500 is a good range. So how we test those is there are these test kits. There's lots of different brands of test kits. This is not an advertisement for Salifert, but I prefer the Salifert brand test kits. They provide good resolution and they're pretty reliable. They're not the cheapest though. And each of the test kits is a little bit different. So there are these cards that come with the kit, and I've like laminated them so that they're all waterproof and nice and stuff. Some of the kits are very easy to use. So the nitrate kit And there'll be all these different tests will be on different tables. There's a sample container, and then the instructions tell you what to do, not only written in words, but also a visual diagram. So you take a milliliter of the water you're testing, put it in the container, put 4 drops of the stuff that's in the bottle in the container, and then 1 scoop of the dry chemical. So also inside the box, so you got a milliliter of the water you're testing, 4 drops of this liquid, and it's the same as like saline solution drops. Then there's a dry powder that's in this container. There's a little scoop, so 1 little scoop of that. There's a little scoop in there, 1 level scoop, dump that in the container. So what happens is when you add the test chemical and the dry powder to the water will change color. It'll go from being colorless to being pink. And this little scale here is a comparator scale. So you have it sitting on the table, and you can put the container beside it and look to see which pink relates to it. So in other words, well, it wouldn't be held this way, but on the table, you can set the container and match which level it looks like, and then read the value. If it's actually still clear, that's 0, and that's great. But if it's really dark pink, that's 100. That would be pretty terrible, very high values. So some of them are easy to use. The nitrate turns pink, the phosphate turns blue, and you can read those that way. The magnesium and the calcium work in a different way. They use a process called titration, where you want to read the relative amount of the chemical. So how both the magnesium and the calcium test kit work, I'll like help you out with it, but the instructions on here, they're a little bit more complicated and detailed, but in a way you're going to add 2 chemicals to the water, and then you have to, with another syringe, drop-wise, add some of the 3rd chemical until the water changes color. So what happens is this will start out as being pink, and then you have to add a little bit at a time from another syringe and keep stirring and mixing. And at some point, it'll change from being pink to being blue. It will change rapidly. So it'll be pink, pink, pink. It stays pink. You're still adding dropwise. It's pink. And then all of a sudden, bam, it'll turn blue. And that is actually a pH indicator that has told you that the pH has changed from being acidic to basic. And then once it is at the point, it's called the end point, where it changes from being pink to being blue, you will have used a certain amount of liquid from the syringe. You read the value on the syringe, and then on the test paper, there's a chart. So for instance, you've added the stuff and you're like, oh, this says 0.55. You just look on the chart to see where 0.55 is, which would be like right here. Right beside it gives you a number, and that number is the value for the concentration of either the magnesium or the calcium. So when you see the instructions and you see that, well, at one point the solution looks pink, and then you add some chemical, and then it looks like it changes to blue, you're looking to see at what point does it change blue. And for both the magnesium and calcium, you're actually going to have to use quite a bit. So you should expect that when you start with the whole milliliter of liquid, don't think it's going to change really early on. It's going to change quite a ways into it, at least halfway or 2/3 of the way. Just depends on how the magnesium and calcium are going. Okay, so a couple other words. I'm going to assign you to an aquarium. In other words, we've got the 105-gallon aquarium, the paludarium tank, there's the fish room, the back room, and I don't know, the library tank. I got to see what's up with that. So maybe we will measure that to see how things are going. I'm going to try to get some fish and coral back in that tank this weekend. So then you will have measured things for each of the aquariums. Another thing that's really critical, these test chemicals are poisonous. When you make those water tests in this lab, that water can't go back into the aquariums. You do like a nitrate test, and you're like, oh, I don't want to waste this water. I'll put it back in the aquarium. You can murder everything. So it is critical to know that once you take water out of the tanks, you start doing some chemistry with it, that stuff's going down the drain, and you don't store or use these chemicals near your aquarium. Some people, I know people, it's a terrible habit. They will literally go to their aquarium, with their test kit, and they'll you know, set the vial up on the edge of the aquarium, right? And then they're adding the chemicals to it, and they accidentally knock it in, and that's not good. I'm not saying that all the chemicals are all poisonous enough to kill everything, but you would never want that to happen. So the smart thing to do is have a clean container where you take a sample and then take it somewhere, like to a kitchen sink or a utility sink or somewhere else. Do your test in a remote location, and then properly dispose of it and properly clean this out, because you don't want to have any go back in. They even put a thing right on the side. It'll tell you well, this is just hydrochloric acid, which is no big deal. But this one has sodium hydroxide. These other ones, I don't know. It's on the bigger paper that's on the inside. And each of the tests, this is sold. It has enough for 50 tests. In other words, it comes with enough chemicals to do 50 tests. So if you do it once a week in a year, you got all your magnesium tests you ever need. And these are like $10. So for $10, you test all of your chemicals. Well, you can test all your magnesium for a whole year if you do it every week. For, what's that? Except for 2 weeks. Yeah, people skip it. And I'll be honest, I don't test as frequently as I should. Testing is a little bit tedious. You get a sense as how things are going sometimes, especially when it comes to adding calcium. As long as you're adding calcium at the right rate, the levels stay about the same. You don't have to test quite as often. But there is an important principle in maintaining aquarium systems that you should never dose a chemical unless you've tested for it. In other words, well, I think my calcium level might be low. Maybe I'll add more calcium. Well, maybe the calcium level is too high, and now you've raised it even further than it should be. So you make the test, and then as a result of the test, make decisions about what kind of treatment you want. So I wrote here on the back of the lab the kinds of things that you can do to lower nitrate and phosphate levels, or what you can do to raise magnesium or raise calcium levels. And I'll share with you the chemicals and equipment that we use to be able to make those kind of changes happen. The same kind of tests are available for freshwater aquariums, testing for the amount of waste that's in the water. It's the same with pool testing. Like you may have a pool or work for a pool company, and people will be like, hey, my pool, the water smells, or my water is green, or the water is milky. And that's because you've got this pool, this big open container of water, and stuff can live in it. You can have parasites living in it. You can have algae living in it. You can have precipitation of some other kind of chemical that's going on in the pool. You don't want that to happen. Most people don't want to be, I don't know, swimming with critters and waste and algae. It's just not, I don't know. You want it to be nice and clear. The water in pools looks blue. That's because you usually if you paint the inside of the pool blue, the water looks blue. The water's not really blue. The water should be clear, If you want your water to look green, paint the inside of your pool green. No one would ever paint the inside of their pool green, because then it looks like you got algae in the water.
But it was kind of it was a nice pool, they had rocks there, they were doing
Maybe like a teal green kind of.
They're doing it with it was kind of like a dark green, but it was like a nice pool.
I gotcha, yeah. So it looks more like natural, like a pond, yeah. I mean, you wouldn't painted the inside red. It looked like something got murdered in the water. You also want to be able to see into the water well. Like if you painted the inside of a pool black, you'd never be able to see if anything in the water. You wouldn't know if the water has changed color, somebody's in the water. You just don't know. So pea sharks, yeah. People have there's myths that are pervasive that public pools put something in the water so that if you pee in the water, it changes the water's color. People can tell you peed. That's not a thing. It's it'd be possible to maybe design a thing like that, but you don't do that. That's not really, it's not a deal. Yeah. A lot of people will keep their pools covered, and that helps prevent evaporation. It also prevents like leaves and stuff from getting in, but more importantly, prevents like light from getting in the pool to make the algae grow a lot. And there's real issues with pool safety because you don't want, like, in pretty much every municipality, including the city, if you have a pool, you have to have a fence around it. That prevents like kids from accidentally getting into it. Also, like if a deer falls into the pool, it'll struggle and drown, and now you got a dead deer in your pool, and that's disgusting. Like,
That's why in Florida they have this whole entire thing. You got like a whole, have you seen that? Like a whole enclosure around all
oh
of it,
yeah,
especially when they're on a canal.
yep,
Because alligators will just come straight up out of the canal.
yep. You're like, oh, go in there.
Imagine you about to go for a morning swim.
So a lot of animals can deal with being in water and go to water, but naturally, water doesn't just like drop off with a vertical wall. You know what I'm saying? Like you're a deer, you go up, there's water. It starts out as an inch or two, and you can walk into it and walk back out. But boy, like, and a deer might go up and like put its front hooves in the water and drink. But if you go and put your front hooves in a pool, you're going in. You're not. You're going in. You're going in for a swim, and they're not smart enough to use ladders. They can't. Even if they can get there, even if they get up on there, they're just digging at it. They'll tear your liner out. And yeah, you're like, oh, my pool's half empty. What's up? There's like a dead deer in it. The liner's destroyed. Yeah, it just makes a mess, right? So you put fences around the pool. Some people think you put fences around pool for privacy, and people do have fences that'll be like, full fences so you can't see in. But the purpose is really to prevent, people who aren't supposed to be in deer and stuff from getting in. Because that's a big deal. They said it's cute. You can see videos of like, that no, like what do you call them? Raccoons. Like raccoons will clean their food. I've seen videos of raccoons like taking their food to someone's pool and like cleaning it in the pool and then eating it. That's super cute. That'd be worthwhile. Yeah, they get so confused and it disappears. Where'd it go?
He like gets more. He does like 3 times.
Yeah, there's great videos of making like people and things disappear for dogs and cats and stuff. Like the blanket trick, and then you like run to the side. Didn't care? No. It's cool. It's cute. But a lot of people with their ponds will have the bottom of the pond be black or dark, and that's to help like warm the water up, And then because a lot of ponds have algae, it's better to have the water kind of like be black than look green and gross. And it's hard to keep the bottom of a pond like clean and bright. So most pond liners are just black. That's that. But yeah, swimming pools or whatever, the water in a pool looks whatever color it looks because that's what color you painted the pool, or whatever color the tiles are, or whatever. The Yep. What's it saying? Yeah, I have it in the right format and it's there. Is it the only thing it's set it for? Or I mean, if you have it on paper, you can just turn it in. You know what I mean? Like you don't have to do it in Schoology. The salinity, density, and depth. Yeah. I mean, like I had it for you to pick up a couple days ago. It's the one where you make the graphs. You know what I mean?
Yeah.
'Cause doing it in Schoology is really hard. The only reason it's really in Schoology is for remote students. Let me look and see. Um, fifth. Salinity. Yeah, it's all right. It's in the right format. This is the right message. Let me look in OneDrive. Schoology, OneDrive assignments, section 2, salinity and depth. Yeah, Malik, it shows that you opened it.
This is just what it shows on graph. Oh. Shows you that. And before it said your file had not been created.
Huh. I think it must be a problem. Have you ever gotten that before?
I've got it for 2 of my Spanish assignments, but I don't know how to fix it.
I don't know because like it showed like I can see through OneDrive whether or not a student also like opened it because it creates a file and it shows that you opened it and started creating a file. It says today 10:26, which was 24 minutes ago. Yeah. And this is all set up correctly because it has to be a doc accent. It is that it says this is right. I have a valid date. It's a lab. This is the valid marking period. That's checked. Published to everybody. But you want to do it. Do you have it on paper?
I don't think so. I'm gonna try to go into it.
All right. You want to do it on paper anyway because it's on. Let me find. Maybe it's here. So many papers. We'll be Schoology experts next year. Here's a paper copy. That's the easiest way to do it because there's graphs to do and you can't do them in there. 4 minutes. Stabler, Ransom, Kurtz, Tillotson, Gonzalez, Clarity. Ooh. Just turn this in. Same plan.